Okay, so let's try to apply what we just learned to another problem. So let's say we had 2x to the fifth plus 7x to the fourth minus 18x squared minus 8x plus 8 equals 0. And we want to solve for x. We want to find values of x that make this equation equal 0. So what we could do is first apply the rational zero theorem. So we look at the leading coefficient, which is 2, and we look at the constant term, which is 8. Okay, so we know that all the rational zeros are going to have this form. Okay, they're going to be either, so we have the factors of 8, so plus or minus 1, plus or minus 2, plus or minus 4, or plus or minus 8. And then we have the factors of the leading coefficient, so plus or minus 1 or plus or minus 2. Okay, so we can list those all out. So plus or minus 1 divided by 1, so that's plus or minus 1, plus or minus a half. Okay, and we have plus or minus 2. We've kind of already accounted for plus or minus 1, so we don't need to worry about that. Plus or minus 4, and again, we've kind of already accounted for plus or minus 2, and plus or minus 8. Okay, so those are the possible rational zeros. And then maybe we want to look at where those rational zeros are going to occur. So, we know kind of when to stop looking, either at positive ones or at negative ones. So we can see in the original form of this function, we've got no sign change here, but we have a sign change here. No sign change here, but then we have another sign change here. Okay, so we have two sign changes. That means we're going to have either 2 or 0 real positive roots. Okay. Then the same thing, we'll look at the sort of negative version of it. So we'll look at 2 times negative x to the fifth plus 7 negative x to the fourth minus 18 negative x, negative x squared minus 8 times negative x plus 8. And we have negative 2x to the fifth plus 7x to the fourth minus 18x squared plus 8x plus 8. Okay, so we have 1, 2, 3 sign changes. So we're going to have either 3 or 1 real negative roots. Okay, so maybe that'll be helpful, maybe it won't, but it's good to know either way. So from there, we can kind of just start checking. Now, you can always use a graphing calculator, either one that you access online or if you have one at home, to kind of predict, get a sense of what the graph looks like and where you really want to look for those roots to confirm them. So you can plug in 2x to the fifth plus 7x to the fourth minus 18x squared minus 8x plus 8. And if we graph it, this is also just kind of a crazy looking graph. So it's kind of cool to look at. So if we look kind of at the shape of what this graph looks like in the window, we notice that we have this little, almost little peak right here. And it looks like it's about at -2. Now, anytime you have a little peak or a little valley like that that seems like it's hanging on or sitting on the x-axis, That's a place where you have either a double or quadruple or some kind of root of multiplicity more than 1. So we're going to look at that kind of closely as we're testing. Then from there, it looks like maybe negative 1.5, although we're not quite sure. That wasn't really one of the options, so probably not, probably something else. Then we look here, we look like we're maybe at positive 1/2. And then here it looks like maybe we've got 1.5, or maybe we've got something else. So we'll kind of see how it shakes out. Now, an important thing to notice, remember Descartes' rule of signs predicted either 3 or 1 real negative roots. And see here, we've got one kind of normal root here, and then we've got a root here that we know has to be a multiplicity 2 because it's kind of hanging from the x-axis. So we've got our 3 roots. We've got 2 of them right here, and we've got 1 of them here. And then it predicted 2 or 0 positive real roots, and notice we've got 2 positive real roots. We just aren't sure quite yet what they are. So to figure out what they are, we can, of course, resort to synthetic substitution. Now, first, we're pretty sure that -2 is going to be one of those roots. So we want to try -2. And remember, as we copy our polynomial down here, we're going to do 2, because that's 2x to the 5th. We're going to do 7. We don't have an x cubed term, but we're going to still put a 0 in there for our x cubed term's coefficient. Then we have -18, we have -8, and we have 8. Okay, so we're going to try our synthetic substitution there. Bring down this 2. 2 times -2 gives us -4. 7 minus 4 gives us 3. 3 times -2 gives us -6. The -6 just comes down. We get 12. That gives us, again, -6. -6 times -2 gives us positive 12. 12 minus 8 gives us 4. 4 times -2 gives us -8 and 0, so our remainder is 0. So yeah, -2 definitely is a root. Now remember, we were thinking that not only was -2 a root, it was maybe a root of multiplicity 2. So that means that -2 is also going to be a root of whatever we have left behind here, okay? So we can just keep this synthetic substitution train going. So we bring the 2 down. 2 times -2 again gives us -4. 3 minus 4, -1. This gives us positive 2. Okay, so -4, positive 8, 2, -4, 0, and 0, 0. So yeah, -2 is not only a root, it's a double root, because not only is our remainder here 0, we get our kind of second term here is also 0. So from there, we can kind of deal with maybe any other guesses we had. Now remember, these other values, so this looks maybe like it's about 1.5, and this looks maybe like it's about, -1.5 and positive 1.5. But remember, those were not possibilities for our rational zeros, okay? So there's something else going on there, maybe something irrational, maybe a square root. So we want to try possibilities that do fit into this category here. So maybe we'll try 1/2, okay? So if we try 1/2, okay, if we try 1/2, remember, you can do synthetic substitution even with fractions. So we'll bring down this 2. 2 times 1/2 is going to give us 1. -1 and 1 will give us 0. Okay, that's going to give us 0. We're going to have -4. -4 times 1/2 is going to give us -2, and that's going to give us 0, and 0 out the whole rest. So yeah, 1/2 is also a solution. Now, we still have those two probably irrational solutions to deal with. So how do we do that? So now that we have this kind of partially factored form, what we can do is write it out. So x plus 2 is going to be a factor of our original equation here. And because it's a double root, because we have negative 2 as a root twice, we can write x plus 2 squared, okay? 1/2 is also a root, so we can have x minus 1/2, okay? That leaves the question of what's left over. And what's left over, remember, our original polynomial was of degree 5, and we've taken, in a sense, 3 degrees away. We have an x squared that we've taken away, and we have an x that we've taken away. So our leading power, or our degree of whatever's left over, is going to be x squared. We can look down here. So we're going to have 2x squared plus 0x minus 4. Okay? So we'll have 2x squared plus 0x minus 4. And that equals 0. So the question here is, how do we get those irrational roots that we were wondering about here? And notice this isn't quite perfectly a difference of squares. We can factor a 2 out. Okay, so we can have 2x plus 2 squared times x minus 1/2 times x squared minus 2 equals 0. And again, this isn't a difference of squares, but we can still kind of treat it or factor it like a difference of squares. So we'd take the square root of this and the square root of this, and we're left with 2 times x plus 2 squared times x minus 1/2. And then we'll have x minus square root of 2 and x plus square root of 2 equals 0. Okay, and we can check that on our graph. Okay, we'll calculate the value when x is negative 2, 0, that's good. We'll do it when x is negative square root of 2, 0. We'll do it when x is 0.5, 0. And we'll do it when x is positive square root of 2. And again, we get 0. Okay, so those are all of our possible x values. So x equals negative 2, negative square root of 2, 1/2, and positive square root of 2. Now this is a double root. So these 4 distinct answers account for the 5 possible zeros that we can have to this polynomial.